existe una unidad de servicios médicos por alguna emergencia. Si alguien tuviera algún problema de salud, reportarse por favor con las edecanes del staff para que sean conducidos a la enfermería. Bueno, después de esto les doy la cordial bienvenida y los invito a escuchar la conferencia magistral del Dr. Baum. Gracias.
Pero ahí Billy, le gusta, por cierto, que le digan Billy, él enfrentó su primera elección entre pasársela muy bien en Europa o regresar a trabajar duro a Harvard, y optó por la segunda opción, mostrando un autocontrol definitivo. Y ahí fue profesor, fue becario, posgrado por 3 años y después profesor asistente por otros 4 años. Posteriormente, el Dr. Baum se movió a Maryland, a un instituto de evolución, cerebro y conducta por 2 años. Posteriormente, él ingresa a la Universidad de New Hampshire en 1977 y permanece como profesor desde 1977 a 1999. Yo tuve la oportunidad de disfrutar su asesoría del año de 88 a 1992, él fue mi director de doctorado. Después el doctor Baum se retira en 1999. Para darles una idea, el doctor Baum se ha distinguido por muchas contribuciones, un trabajo muy importante en elección. Fue publicado en 1974, donde él presenta 2 desviaciones de la ley de igualación. Este artículo es uno de los artículos más citados en conducta de elección desde aquel entonces. Además, el doctor Baum es de los primeros investigadores con énfasis más ecológico a la situación experimental, estudiando requisitos de viaje, requisitos de traslado, modificando la cámara experimental. En una de sus anécdotas, él vivía en Cambridge y había un hoyo en el techo del edificio y se llevó un equipo electromecánico de la universidad y lo colocó en el ático y puso un panel para pichones. Y entonces había una serie de pichones que ahí llegaban y él estudió la ley de igualación en vez de contar respuestas, contando el número de pichones, demostrando la igualación que posteriormente sirvió para hablar de la distribución ideal libre. Él siempre se ha distinguido por modificar la situación experimental, requisitos de traslado y costo. Mi tesis de doctorado fue una simulación operante de forrajeo. Y Billy Baum, para darles una idea, se retiró en el 99 y desde el 99 a la fecha solamente ha publicado 69 artículos desde que se retiró. No hay que contar los que antes, a partir de que se retiró son 69 artículos. Entonces, para mí es un placer, es un honor, sobre todo porque el doctor Baum ha venido en muchas ocasiones a Guadalajara. Cuando yo estuve aquí como profesor, él trabajó con nosotros, con nuestros estudiantes. El doctor Cabrera recibió fuertes influencias de él. Debo mencionar que hay un libro muy importante del doctor Baum que se llama Entendiendo el conductismo, se llama Evolución, Conducta y Cultura. El doctor Raúl Ávila en la Universidad de la UNAM tiene una traducción al español que tiene muchos años trabajando en ella, bastante buena. Y es un libro muy interesante para ver la relación entre la biología y la psicología. Y es de lo que nos va a hablar el día de hoy. Por favor, ayúdenme a darle la bienvenida al doctor William Baum.
There's a clock up there, actually. Yeah, all right. Well, those of you who are standing in the back, there are some seats up front here. So you can sit. All right. Well, thank you, Carlos. Thank you for having me here, and I thank all of you for coming to hear what I have to say. I'm going to tell you about a new way of thinking about behavior I've been working on for some time now. And I'm going to tell you about 3 laws of behavior that I call the Law of Allocation, the Law of Induction, and the Law of Covariance. Okay, well, I may have to rely on you. Yeah. So everything I'm going to say today stems from evolutionary theory, because it is not possible to understand behavior in a sensible way without evolutionary theory. And yeah. Okay, so first, well, this will work. Whoops, going too far. Okay, there. This works. So first I'm going to tell you about what behavior is from an ontological point of view, and therefore how we should measure it. And that will lead us to thinking about behavior as continuous. Oh, no, what happened? Okay, as a flow, and that will lead us to the law of allocation, and I'm going to explain that the law of allocation holds at every time scale, no matter how small we're talking about. And then I'm going to talk about the function of behavior in an evolutionary framework, and that will lead us to what I call phylogenetically important events. And I'll emphasize that they're phylogenetically important. You can't leave out the phylogenetically part, because it means if an event is important in phylogeny, it means that it has an effect on whether an organism will reproduce or not. And that will lead us to the concept of induction, and then I will talk about the law of covariance, which has to do with adaptation. Oh. Well, let's see if this works. No, this doesn't work. Okay. Okay. All right. So next slide. All right, so behavior is process. Now, what process means is change through time. So you think of behavior as flow. That is like a river here, you know? And that means that behavior takes time. Right? There are other reasons why you have to think behavior takes time, but this is a very basic one. Behavior takes time, and that means that when we measure behavior, we measure time. And we should also know that the activities, and by the way, so I call the unit of behavior an activity. All right? I'm not going to be using the word response. I'll be talking about activities, because activities are extended in time. And all the activities that occur take up all the time available. And time is limited, right? There are only 24 hours in a day. and in a month, and so on. And so that means that activities must compete for the time available, the limited time available. Next slide. So that leads us to this law of allocation. So I can designate the time spent in any activity as B sub I, and express it relative to the total time taken up by all the activities, right? That's all the time available, and write this equation. The relative time spent in an activity out of all the time is equal to its relative competitive weight. So V sub I relative to the sum of all the competitive weights. Now, what do we mean by competitive weight? By competitive weight, we mean things that are commonly called consequences, so-called reinforcers, but I'm going to be talking about induction. So competitive weight is the result of induction. It may be strong induction, it may be weak induction, and that's what makes competitive weight vary. And of course, the more is the competitive weight of an activity, the more time it takes up. Next slide. So here's a way of visualizing all this. Suppose we keep track of 4 activities: gaining resources, socializing, maintaining health, and maintaining and spending time with family. Now, each of these upturns here is an episode of that activity, and this shows the 4 activities over 4 days. And then we can summarize this in a pie chart like this. So you can see that most activity was spent in maintaining health, and then you see here the red is a lot of time spent gaining resources, family, and socializing is the green one. So that's a way of looking at behaviors over time. So we accumulate. Next slide, please. And here are some actual data. I got these from the U.S. Bureau of Labor Statistics. This is time spent in 2015 by civilians 15 and older, and they had a lot of categories, and I did collapse some of their categories. But you can see that the large majority of the time is spent in health maintenance, and then this pink one is gaining resources. This red one is reproductive activities like family and tending to children and so on. The green is relationships. Now, notice what I did. I took this one, gaining resources, and I broke it out into its parts. And this is working, right? The yellow. And so that's part of gaining resources, eating, shopping, buying things, and educational activities I put in there also. So you see that an activity can be broken apart into its parts, which also are activities. Next slide, please. And so what I want to emphasize here is that allocation occurs at any time scale, and that's because some activities take longer than others, right? It takes longer to read a book than to read a chapter in the book. It takes longer to love someone than to kiss someone, and it takes longer to believe something than to avow that you believe that thing. And so as we go from one to the other, we're changing time scale. These reading a chapter, it's on a smaller time scale than reading the book, which is on a longer time scale. And the relation of these activities that make up a longer time scale one are part-whole relationships. So these are parts and wholes. For those of you who know philosophical jargon, these are mereological relations. So the parts, the activities that are parts of a longer one sum to the time of the whole. And because there's always a time limit, the parts of any activity compete for time. And so we could take any activity we care to and look at it this way. For example, practicing ballet, which is something I've never done. But I have served a tennis ball, and I know about that. So serving a tennis ball has very short time scale parts. You toss the ball in the air, you raise yourself up, you lift your racket up, you bring the racket down. So all of those are the parts of serving a tennis ball. And of course, serving a tennis ball is part of playing tennis, right? Which is a longer scale activity. And of course, we're all familiar with time management, I'm sure, or you should be if you're not. And it's a question of, how will I allocate my time? When will I spend time studying? When will I be out with my friends? And so on. Next slide, please. So just to drive this home, here's another way of looking at it. Suppose we keep track of 4 activities: professional activities, householding activities, personal activities, and activities with friends. All right, and here are the times spent. Most time is spent working and professional, and then there's householding activities and personal activities. Now I broke out the personal activities into its parts, okay? So that activity is now got these parts: maintaining health, reading, meditating, cooking, working on the car. You can do this, of course, at home for your own activities and figure this out. But now I'll take one of those, meditating. I'll take that, and it has parts like breathing, chanting, focusing, all right? And you notice that every activity has parts that make it up, and as you go from left to right here, you go from longer to shorter time scale. Next slide, please. Okay, so now that was the law of allocation, and now I want to talk about the law of induction, right? And the law of induction says that behavior is induced by phylogenetically important events, or we can abbreviate it, PIE. Induction is a feature of organisms. Now, it's not the same as elicitation. Elicitation is an older concept, related perhaps, but elicitation is conceived in a very small time frame, and usually a kind of one-to-one relation between a stimulus and a response. But here we're talking, first of all, we're talking about extended time, activities that are extended in time, and they are induced by these phylogenetically important events. That concept of induction was introduced in 1972 by Eve Siegel, and the way she conceived of it was as a process that's extended in time. And so I'm going to talk about induction, but first we have to understand where it comes from in terms of evolutionary theory. So we ask the question, what are organisms good for? Next slide, please. So the function of organisms may be thought of this way, as an interactor that's carrying a replicator. Now this terminology was invented by David Hull, a philosopher of biology. And the replicator, the idea is the thing that gets copied. And of course, we think right away of DNA. So the interactor is carrying around the replicator, and this arrangement has advantages for the replicator. Having that interactor means that the replicator is protected. It's defended in many ways, including the immune system, for example, which is fending off an onslaught of the less organized life forms like bacteria and viruses. We're constantly competing with these less organized life forms. And so the interactor provides both physiological mechanisms, which I won't talk about today, but also behavior. Very, very important for the replicator. So the concept involved here is, if you ask the question, well, why are there organisms at all? The answer is that organism-making genes, the genes that would make an organism rather than, let's say, a bacterium, were selected because they result in more faithful copies of the replicator, the DNA. And of course, that is represented in offspring. So it's actually fair to say that the organism is DNA's way of making more DNA. That's what an organism is, actually. Next slide, please. So this is the kind of arrangement that we see. A replicator that's carrying around the DNA, so this is very advantageous for the DNA, as you can imagine, and the interactor has this function. Next slide, please. And so the interactor has the function that it reproduces. That's its ultimate function, reproducing. And that's its activity. And everything else that the interactor does is part of reproducing. Next slide, please. So we think then about the functions of behavior within this context. Well, as I said, the ultimate function is reproducing. And behavior deals with events that affect reproducing one way or the other. Events may enhance reproducing, they may also threaten it. And so these events I call phylogenetically important events, PIE. And the examples are a potential mate, a prey item, a predator is a PIE, right? And you'll notice that some of these are good and some of these are bad, in the sense that the good ones are the ones that enhance the likelihood of reproducing, like encountering a potential mate or prey, but other ones are bad in the sense that they threaten reproducing, like encountering a predator. And so the PIEs induce activities that are parts of reproducing. A mate induces courtship, and prey induces capturing and eating. A predator induces hiding or fleeing. And you can see that these activities then act back on the event, the PIE, either to enhance the likelihood of reproducing, courtship does that, or eating when you encounter food, but hiding and fleeing, that reduces the threat of a bad PIE. So these activities, right away, they affect the phylogenetically important event itself, and that makes sense because that would be the result of selection, natural selection acting on populations. Next slide, please. So these are examples I'll run through. Potential mate. Next slide, please. Offspring, of course, PIEs. Next slide. Prey items, PIE. Next slide, please. Human prey are very varied, of course. Next slide. But other species, other kinds of prey, and of course, water, and for birds, often nest site as a PIE. Next slide. And then on the other side, we have the threatening PIEs, injury, of course, and that induces avoidance. Next slide, please. Heights are threatening to reproduction. Next slide. Predators, of course. Next slide. Toxic organisms. Next slide. And in our species, we have lots of social PIEs because the human face is an extraordinary organ. It has many, many muscles and allows a huge variety of expressions. But these are really good examples. The smile, laughter. Have you ever wondered why we laugh? It's strange if you really look at it, you know. Why do we make that noise? Well, it seems to signal sympathy and accord, but even people who are blind from birth smile and laugh. So it's a definite response to other people. Next slide, please. Of course, there's the other side of these social PIEs, the ones that threaten our relationships with others. Next slide. And I don't want to leave out imitation, in which a model induces similar behavior in an observer. And that's very often a grown-up and a child, but there are other possibilities as well, adults imitating one another. We're a highly social species. Next slide, please. So to summarize this bit, the advantage of behavior is that it serves to change the environment in ways that promote reproductive success, in ways that promote reproducing or prevent it from not happening. And so these induced activities mitigate bad PIEs, like they hide or flee from a predator or defend, enhance good PIEs, like a mate, foraging for food, protecting offspring. And all of these activities we can see are due to natural selection, to phylogeny. Because if you imagine a population in which these activities were weak or absent, the individuals that would behave this way would leave more surviving offspring. So these we can attribute to natural selection. But I also want to talk about ontogeny, or what we can call adaptation. That is, change in behavior within a lifetime. Next slide, please. And that brings us to the law of covariance. Now, induction is the result of environmental covariance. We can think of covariance as occurring in evolutionary time in phylogeny, and that leads to natural selection. But we can also think of covariance in ontogeny, that is within an individual organism's lifetime, and that leads to what we usually call adaptation. Next slide, please. And adaptation can be understood as behavioral plasticity. It's actually a type of phenotypic plasticity, if you think of behavior as part of phenotype. I do not use the word learning. It's a terrible word. It has way too many connotations and too much history. Rather, what I say is that behavior is sensitive to correlations in the environment. There's regularities in the environment to determine behavior. And there are things like if a location is correlated with prey, that leads to approach and visiting that location. If a location is correlated with predators, that will induce avoidance of that location. And I want to emphasize that the natural selection and also this behavioral plasticity, these occur on average and in the long run. They're the result of a process going on over time. What has to be true is that the probability of success is greater than the probability of failure. And if there are variants within a population of organisms or a population of variant activities that have a greater probability of success than failure, those will be selected. And I'll use correlation and covariance pretty much interchangeably, but I prefer covariance because it has less baggage attached to it. Next slide, please. So here's how we can think about adaptation as it's affected by covariance. Now, there are two kinds of covariance that affect behavior. One is covariance between a stimulus, some environmental event, and a PIE, a phylogenetically important event. And the result of that, when there's covariance like that, the result is that the stimulus induces the activity that the phylogenetically important event induces, and you'll recognize that as sometimes referred to as a conditional stimulus, or it's also the same as a discriminative stimulus. So whenever we talk about stimulus control, we're really talking about covariance between a stimulus and a phylogenetically important event. And that stimulus induces the same behavior. But those of you who get a little worried about stimulus substitution here, I'm not talking about stimulus substitution, Pavlov's theory. Rather, I'm saying something quite a bit more general. So the other kind of covariance is covariance between an activity and a PIE, and that covariance results in the PIE inducing that activity, right? Something like lever pressing producing food, and the food induces the lever pressing. This activity we have called for many years operant activity. Notice I use the word operant only as an adjective. I do not use it as a noun. Okay. An example is, let's say, pecking in pigeons. It's a nice example. It's been researched a lot. It's definitely induced by food. If you put a pigeon in a chamber and do nothing, after a while the pigeon just kind of settles down. But then if you start putting in bits of food, it becomes very active. Does a lot of different things, engages in a lot of different activities, but very often, typically, it will peck. It'll peck at anything. It'll peck at a screw in the wall. It'll peck at a key, of course, a lit key, and it will peck in the air even. So pecking is induced by food, but we can also make pecking an operant behavior, operant activity, if we arrange that its pecks produce food. So then the pecks produce the food, and the food induces the pecking. We can also put it under stimulus control, which is the stimulus PIE covariance. And let's say we covary a red key with food and a green key with no food, then the pigeon comes to peck only at the red key. Call that a discrimination. A everyday example might be encountering a potential mate. That induces sexual arousal. You can attribute that to natural selection, but it also entails operant behavior that we call dating, courtship, of course, and then it comes under stimulus control of rules. Rules are discriminative stimuli, and these are mostly aimed at coercion avoidance, what you should and should not do. Next slide, please. So just to make this as clear as I can, here's the first kind, the signal PIE covariance that results in a conditional inducer, and we can think of these as being both positive and negative. A positive one means that if you look at the rate of the PIE, when the signal is absent, it's low. When the signal is present, it's high. And that's a positive covariance. And examples are things like a warning signal of predators, parasites are covary with illness, money covaries with food and other goods, a gun covaries with injury. But also, these can be negative. In that case, when the signal is absent, the rate of the PIE is high. When the signal is present, the rate is low. And examples of that are something like distance away of a predator and the likelihood of encountering it, parasites and mating. The more parasites you have, the less likely you are to mate. And of course, when it gets to winter, food becomes scarce. Next slide, please. So the simplest kind of covariance that I think you can think of is pairing. And you can see here, this elephant will probably be much more cautious the next time that it approaches this water hole, as you can see. Next slide, please. And so maybe the crocodile also will be more cautious too. But there are many forms of this kind of covariance, these simple ones. Here's a more complicated one. Next slide. Recognizing a person from a figure. So the teacher here is saying, Mrs. Hammond, I'd know you anywhere from little Billy's portrait of you. I think this slide is very funny, but maybe you don't. Okay, next slide, please. Now, the second kind of covariance, which is operant activity, we have the rate, the PIE rate on the vertical here, and the rate of the behavior here. We say sometimes the behavior produces or leads to the PIE, and the blue line is showing you a perfect relation, which we model in the laboratory with a ratio schedule. So the more the behavior, the more the PIE occurs. And the red is no relation, and the black curve shows you what happens when there's an upper limit to how often the PIE can occur. We model that in the laboratory with an interval schedule. And examples are things like foraging and food. The more you forage, the more food you get. Courtship and mating, the more you court, the more you mate. Digging a burrow, and work, the more you work, the more food and other goods you get. Next slide, please. So here's, I want to emphasize this one because it may be a little strange to you. So think here on the left of induction. The environment produces, affords some stimulus, let's say food, and it impinges on the organism, and that induces a variety of activities, as I was telling you about the pigeon, for example. A variety of activities are induced, all right? And that's just induction, pure and simple. But now, if we create a contingency, that is, if we take one of those behaviors, the one I call B, and let's say it's pressing a lever, and have it produce, affect the environment so as to produce the food, then you see we have closed a loop here. The activity produces the food induces the activity, and by the way, notice it continues to induce to some extent some other activities too, not just the operant activity. But now it induces the operant activity. So the contingency closes a loop, and the food induces the activity, and the activity produces the food, and then the food induces the activity, and so on, round and round. And what I want you to notice is that the distinction here between antecedent and consequence disappears, right? Because the behavior is as much follows as precedes the food, the PIE, right? So it's a mistake, I think, to talk about consequences, even though, of course, everybody does. Next slide, please. And just to be complete about this, you can also have negative covariance between PIE rate and some activity. Then, of course, we start talking about avoiding if it's a bad PIE. If it's a good PIE, we talk about failing. And so the same three, perfect is like a ratio schedule. This curve is like an interval schedule, and of course the red line means there's no relation. And examples, if you hide, you may be less likely to be eaten by a predator. If you're clumsy, like a young cheetah, for example, dealing with prey, that's an example of failing. Finickiness avoids illness. Human poison avoidance. I'm sure there are people in this room who have food aversions that they acquired because they ate something and got ill afterwards. You were throwing up all night, and boy, you do not want to eat that thing again. And then, of course, aggression will tend to remove predators. Next slide, please. So what I want to draw your attention to is that that covariance of this sort actually is a basis of selection. Every Darwinian process consists of three elements. Variation, which occurs within a population or a pool. Think of a population of mice, for example, and a pool of behavior. So all the various behavior that one engages in. And the second is recurrence through time. That is, whatever it is that can be selected must recur through time. So, of course, in offspring, when we're talking about natural selection, but when we're talking about behavioral selection, we often talk about habit, for example, the tendency of behavior to repeat through time. And the third element is selection. And selection just means that there's differential recurrence, all right? And what I'm pointing to here is when we're talking about selecting behavior, it's differential induction. That is, some behavior is induced more strongly than another. What that will do is it will increase the frequency of that activity relative to others. And remember that activities compete for time. So if one activity increases in time, others must decrease. So we can think of selection as phylogenetic covariance, in which case we're talking about some trait covarying with fitness, and the example I've been talking about is PIE-induced activity, which will definitely covary with fitness, that is reproductive success. But I want to really emphasize here now ontogenetic covariance, and we've seen the two kinds. Covariance between a signal and an inducer, which results in a conditional inducer. The signal is a conditional inducer. And the second kind is covariance between an activity and an inducer, and that results in operant activity. The activity is operant activity in that case. Next slide, please. Now, when you impose a contingency, it has two effects. First of all, if there is no contingency as a baseline, and you have the rate of the induced activity, operant activity, let's call it lever pressing, and on the vertical, the rate of the PIE, let's say food. If there's no contingency in baseline, you're going to get a lot of eating and not much pressing. All right? But now, if you impose a contingency, this line here, let's say, is like a ratio schedule of FR10. So let's say the rat now has to press the lever 10 times in order to get a bit of food. All right? That means that this is no longer possible, because every combination of pressing and food must lie on this line. Next slide, please. So that covariance which this line represents constrains what's possible. And what typically happens, next slide, what typically happens is that the performance moves from this baseline to some point in the middle on this line here. And I review this diagram here just to give you the sense of that. And so, next slide, please. Typically, historically, you might say this would be called reinforcement. I put it in scare quotes because I don't like to use the word. Next slide, please. but you get a reduction in the rate of the PIE. So you might have to say, if you were going to be consistent, that this contingency punished the rate of feeding. I don't think that's a very sensible way of looking at it, but that is what you'd have to say. Next slide, please. And the point I want to make here is that the covariance connects. That is to say, now the lever pressing is operant behavior, and the PIE, let's say the food, induces it now. Next slide, please. So covariance selects operant behavior, and the basis of that is that this B star, I'm calling the operant behavior, produces the PIE. A B star is required, it's necessary. The PIE doesn't occur without it, and that's how it gets selected. So the PI induces the operant behavior, but not other variants. It's specific because other variants are not necessary and will occur, at random. And so we get differential induction of what we call operant behavior. And you can compare that with the differential reproduction in natural selection. Next slide, please. So what I have said is that in order to explain allocation and change of allocation, change in the frequency of any behavior, is we have two laws. Induction, that the PIEs and their proxies, the signals that are covary with them, induce activities, both non-operant, what we often call adjunctive behavior, and also operant, all right, both. And then covariance, which selects activities as a result of the activities covarying with PIEs. Next slide, please. So here's what I have told you. I told you there are three laws. Our law of allocation tells you what to measure because behavior is continuous flow. Activities are extended in time. Activities compete for time. And you should be measuring relative time spent and taken up by an activity. And induction, what's colloquially called consequences, that occurs both in due to phylogeny and occurs in ontogeny. Phylogenetically important events induce activities. Induced activities include both operant activities and adjunctive activities. And finally, the law of covariance, which explains adaptation to a changing environment. And here we have two kinds. An activity covarying with a PIE, and that's operant activity, and a signal covarying with a PIE, and that's what we have called in the past stimulus control. Next slide, please. And I thank you for your attention. Yeah, we do have a little time for questions. Yes, so there's a microphone for anyone who wants to ask a question.
Si alguien tiene preguntas, levante la mano y le llevo el micrófono.
And if you ask a question in Spanish, Carlos will interpret.
Excelente conferencia. Gracias, doctor Billy. La pregunta va en este sentido. Hace muchos años, junto con Carlos, aprendimos el concepto de distribución. Y la pregunta ahora, después de tantos años, es si es posible aplicar este concepto al espacio. ¿Sí? ¿A dónde ocurren? Al lugar donde ocurre nuestro comportamiento. Por favor, Carlos.
Several years ago, we learned the concept of distribution, and the question is now how distribution applies to space, allocation of behavior with respect to space.
With respect to state.
Geography, yeah.
Oh, okay. Distribution with
Of
respect to
behavior
state.
with respect to space.
Right. Yeah. By distribution, I think you mean what I call allocation, the distribution of behavior among alternatives. Is that correct?
About the space, the physical space. Behavior competes
Oh,
for
yeah.
time,
Right. I see.
but behavior occurs in space.
Oh, right. Yeah. So you could think of an activity as occurring in many different locations, and then each location, whatever activity occurs in each location, would be a part of that whole activity. So you might, let's say, foraging, for example, is an activity, but it occurs in many different locations. So foraging in a particular location would be part of the activity of foraging. Does that answer?
For example, in foraging, you have one space, but you can't allocation this space in 2 parts, 3 parts, in one space. Physical space.
Yeah. Space.
You need
Right.
your behavior allocate in this space your responses.
Yes.
And when you're talking about time, I am thinking if you can't make the same thing with a physical space, relative space for one activity, for another activity, in one physical space.
Well, when you say one physical space, though, you mean in parts, or the space is divided up?
Many
or?
patches, for example, in one forest, for example, with many patches.
Right. Okay, there. So let's say we're dealing with a forest with many patches in which a predator may forage, and so foraging in that forest is one activity. Foraging in, let's say, the particular patch that's in the northeast of that's an activity that's part of foraging in that forest. And the same with foraging at other locations. So that's the way I would think about that. And of course, there's a total of time spent foraging, and the foraging in the different places will add up to the total time foraging. So the different foraging in the different places, those parts of the activity of foraging, they compete with one another for time. So if one patch pays off better than another, that patch will have more competitive weight and will induce visiting there more often and for longer, perhaps, than another patch that has fewer prey. Does that answer your question? Other questions? Yeah. In Spanish or English, Ricardo?
I can ask you in English.
Okay.
So thanks really for your presentation, very nice, and I enjoyed it very much. I want to ask you about, you can elaborate a little bit more on your reluctance to use the term reinforcement, because I'm trying to remember on the literature, on Pavlovian conditioning, for instance, people working in this area, they are not, they are like, they want to talk about the US as a consequence or even as a reinforcer. And all of them know that, of course, there is no causal relationship between the antecedent and the consequence. But so I don't know what is your point, why you don't want to use the term reinforcement or the word reinforcer,
Yeah.
if it is something due to the causality between events or what?
Well, actually, it's due to the metaphor of strengthening. Reinforce means to strengthen. And what I'm proposing here does not involve the concept of strengthening at all. The behavior increases, it decreases, but there's no strengthening here. So I wouldn't want to call a PIE a reinforcer because it's an inducer. Does that make sense?
Yeah, I understand. I can, but in a way you are saying that the contingency or the correlation or the correlation, whatever, what it closes this loop. And this loop, in fact, what is producing is an increase or a decrease in the behavior or the activity that is producing. So is that not strengthening? It's not the same, when we measure behavior, it's not an index of strength or weak when something increases or decreases.
Well, what's strengthened? See, the problem is when you talk about strength, what is it? What's strengthened? I don't know what's strengthened. Skinner talked about response strength. Thorndike talks about the strength of a connection, but I'm not talking about either of those. And so when I say behavior increases, it's gratuitous to say that it's strengthened.
It's allocation, an increased allocation.
Yeah,
Right.
increased allocation.
You spend more
and
time doing it
activity.
because of that event, that
Right.
favorable event, if you will.
Yeah, favorable is not bad. I said, good PIE, but you're absolutely right. Then if the behavior is induced strongly, it will take up more time, and there's another. I think language matters quite a lot. So I don't say the organism spends more time. I say the activity takes up more time. There's a subtle difference, but I think an important one.
Bueno, muchas gracias. Vamos a tener que parar en este momento porque van a dividir en dos áreas.
Where is this person?
Si ya tienen alguna otra pregunta, el doctor Baum puede platicar con ustedes en el intermedio que tenemos. Muchísimas gracias y les pido un aplauso para el doctor Baum.
Oh, I see. Yeah.
Continuamos también con conferencias en el auditorio D, para que los que quieran asistir al área de los auditorios D, y aquí arrancamos en 10 minutos, si gustan.